In this video, we're going to look at Lagrange multipliers. And so what the Lagrange multipliers are going to do for us is to help solve optimization problems with one constraint and also when we have two constraints. So let's take a look at an optimization problem we would have seen in Calculus 1. A rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other three sides. Given that you have 100 feet of wire fencing, determine the dimensions that would create a garden with a maximum area. And then what is the maximum area? So in Calculus 1, we would have said, okay, area is equal to x times y. And they're telling us here's x and here's y. They also tell us that based on this drawing, the way that we labeled x and y, that 2x plus y is going to give us 100 feet of fencing. Then what we would do is we'd solve for y here, and we'd say y is equal to 100 minus 2x. And we'd have a of x. Now we have a function, the area is a function of x. And we'd say x multiplied by 100 minus 2x, and we may or may not have multiplied it through. If we did, we would have had 100 minus 2x squared. And then what we would have said is, hey, let's take the derivative and set the derivative equal to 0, and this is the location at which I have a maxima or a minima. These are my critical points. Now, I'm not guaranteed a maxima or minima, as we know from Calculus 1. It's just that's where my critical points would be. And so we would say a prime of x is equal to, and there should be an x on there, 100 minus 4x. We set this 4x is equal to 100. We would have set that equal to 0 and solved. And so we would have got x is equal to 25. And if x is equal to 25, y would have been 50. And the maximum area A of x would have gave us a max area of 2550 feet squared. And then here's our dimensions. So I know I went through this fairly fast, and that's because this is a nice refresher of a Calculus 1 optimization problem. In fact, we actually would have done this in pre-Calculus 1, in fact, and we would have set this up as a quadratic and found the vertex of the quadratic. So this is something that we would have seen in pre-Calculus 1 and also in Calculus 1. And I'm bringing in something this simple so that it'll help us to look at Lagrange multipliers. Most of the time, though, in this class, because we're in Calc 4, we're going to be looking at more than just x and y. We might be looking at x, y, and z. And in Calc 4, we don't do this replacement here, which is actually kind of nice. So our warm-up was an applied situation involving maximizing the area of a garden, subject to certain constraints. And the constraints are the limits on the optimization. In our case, the constraint was 2x plus y is equal to 100. That's our constraint. The constraints involved were the width, and the area was the function in which we had hoped to maximize, so a of x. If we were to look at our warm-up as a f of x, y is equal to x times y. So in other words, I'm not doing it as a function of a single variable. I have a function of two variables. And this being our constraint, then some of the possible level curves and the constraint is graphed. So there's our constraint in orange. And then I set x, y equal to a number of possible values for the range of my function f of x, y. So the one that actually truly happens is the green. So here's our green. And this actually would have been the area of 2550. And some of these other ones would have been any other level curve value in which this would have a range. Of course, we would have had some down here, but I chose positive values because it's an application. We also know from our last section that the maximum happens when my gradient and the vector I'm looking at point in the same or potentially opposite directions, which means the constraint function must be tangent to the objective function. If the two vectors point in the same or possibly opposite directions, then there must be a constant multiplier of one to the other. This is the basic idea of the Lagrange multipliers. So here's our first theorem. Let f and g be two functions, where f could be our optimization function and g is going to be our constraint function. with continuous partial derivatives at every point of some open interval, some open set containing the smooth curve where my g of xy equal to 0. Suppose that f, when restricted to the points on the curve, g xy equals to 0, has a local extrema at this point x naught y naught, such that the gradient of x naught y naught of g does not equal 0, then there must be this lambda called the Lagrange multiplier for which this must hold true. So here is how you're going to do the problem solving with Lagrange multipliers. So now we're looking at optimization with Lagrange multipliers. So determine the objective function and then the constraint. Does the optimization problem ask for maximizing or minimizing the objective function? You're going to set up a system of equations in which we have our gradient of f at x naught y naught is equal to some lambda times the gradient of g of x naught y naught. We also set up our g of x naught y naught to equal 0. And we're going to set up this equation so that we can solve for x naught and y naught. The largest values of f at the solutions in step 3 maximizes. The smallest values minimize. Now, if the problem has two constraints, say g and h, then my gradient of f of x naught y naught is going to be lambda 1 times my gradient of g x naught y naught plus my lambda 2 h of x naught y naught, where g is equal to x naught y naught is equal to 0, and so is x naught y naught. This, of course, can be extended to then 3 space where I have x, y, and z. So let's use the problem solving right here, using the Lagrange multipliers, to our initial example. Now we know what our answer is, so that kind of helps us, but it also helps take something that is pretty straightforward in Calculus 2 or Calculus 1 and even in Pre-Calculus 1 and brings it into a much larger idea, which is the Lagrange multipliers. So our objective function was the f of xy is equal to xy. And our constraint was g of xy is equal to 2x minus or plus 100 minus 100. 2x plus y minus 100, which is basically taking the equation of the line and bringing it and setting it equal to 0. Now we want to maximize, so step 1 is to determine. We're going to maximize it. My gradient of f is going to be the partial derivative of this with respect to x plus the partial derivative of this with respect to y for the I and j components. So I have yi plus xj. The gradient of this function with respect to first x and then y is going to be 2 plus 1, so 2i plus 1j. If we set this equal, now I'm going to actually use x naughts. I'm going to have y naught I plus x naught j is equal to 2 lambda x or I plus lambda j. Now, we know with our constraint gradient, I actually didn't have anything to put in because they were constants. And we also have 2x naught plus y naught minus 100 is equal to 0. Now, because these are equal, these two equations are equal, this x naught has to equal 2 lambda, and this y naught, and this x naught must equal just 1 lambda. So I end up with this equation, x naught is equal to 2 lambda, y naught is equal to 2 lambda, and x naught is equal to lambda. And I also have this other equation. Since this is a system of linear equations with 3 variables and 3 unknowns, I can start doing back substitution. Now, since I know that x naught is equal to lambda, then y naught must be equal to 2 times x naught. So now I've got a replacement. So in this third equation, which is 2x naught plus my y naught is 2x naught, so I have x naught, 2x naught plus 2x naught minus 100 is equal to 0, which gives us 4x naught is equal to 100. So x naught is equal to 25 and y naught is equal to 50. And then here's my maximum area. And just to confirm this is a maxima, we're going to choose some other point that satisfies the constraints. So one point that satisfies the constraints is when x is 10 and y is 60, I get 600. So here's any other random point that satisfies the constraint, which was this. And I can see that this truly is the maxima. So let's look at some examples in which I'm not actually given an application. They're just asking me to use the method of Lagrange multipliers to find the maxima and minima of the values subject to the given constraint. So they don't even tell me if these are maxima or minimas. So here's the function that I'm hoping to maximize or minimize. And this is my g of x, y, and z, which is equal to x squared plus y squared plus 4, or z to the fourth. These are to the fourth, excuse me. These are all to the fourth power. And then minus 1. So that's actually the function there. So don't forget to bring that constant to the other side. Now we're going to go ahead and do our partial derivative. So my gradient of f, which is going to be equal to, and I probably should put x, y, and z, is going to be equal to the vector, which is 2x and 2y and 2z. I'm going to find my gradient of g, and I wrote f, of x, y, and z, which is going to give me 4x cubed plus, well, shouldn't be a plus, I'm writing it in this form, and then I'll have 4y cubed and then 4z cubed. So again, this is my constraint right here, and this is what I'm hoping to optimize. So what I know based on my theorem up above, that my gradient of f is going to be equal to some lambda multiplied by the gradient of g. So my first set of equations then tells me that 2x naught is going to be equal to 4x naught cubed. I have 2y naught is going to be equal to 4y naught cubed. I have 2z naught, and that is also going to be equal to 4z naught cubed. Ooh, times lambda. Don't forget the lambdas. So that tells me for this first one, I'm going to get, I'll bring everything to the right. So I have 0 is equal to lambda 4x naught cubed minus 2x naught. If I factor out a 2x naught, so I'll have 2x naught is equal, and then a parenthesis, and I'm going to have then 2 lambda x squared minus 1. Now I know you're like, well, couldn't I have just divided by the x naught? Well, yeah, but the problem is that when you divide arbitrarily by a variable, you potentially lose a solution. So that's how come I'm not doing that. Now I know that this one is going to produce something similar, and this one is also going to produce something similar. So I'm going to get 0 is equal to 2y naught, and then I'm going to have 2 lambda y naught, don't forget the naught, minus 1, and that's going to be squared, and I'm also going to get 2 z naught, 2 lambda z naught squared minus 1. So I have this equation, I have this equation, I have this equation, and don't forget that I also have the fact that I have the g, my function g has to be set equal to 0, so I have x naught raised to the 4th plus y naught raised to the 4th plus z naught raised to the 4th minus 1 is equal to 0. And here is my fourth equation, because I need 4 equations for 4 unknowns. X naught is the first unknown, y naught is the second, z naught is the third, and lambda is the 4th. So I need 4 equations and 4 unknowns. I have 4 unknowns, so I need 4 equations, or otherwise I'm going to have dependence. And then we're not going to talk about that in terms of our linear algebra. So we're just not going to do that. Okay, so what we have from the first 3 equations is we have x naught could equal 0, or x naught, by setting this 2 lambda x squared naught minus 1 is equal to 0. I'm going to get 1 over the square root of 2 lambda, and plus and minus. And I'm going to get the same thing for my y naught, which could equal 0, and also y naught could equal plus and minus 1 over the square root of 2 lambda. And z naught is equal to 0, or z naught, I wrote a y there, z naught could equal plus and minus 1 over the square root of 2 lambda. Now what we have to do is we have to explore every combination here. So I have x naught is equal to 0 or this, x naught is equal to 0 or this, z naught is equal to 0 or this. So let's start with the lowest hanging fruit, and we're going to initially use this last equation, equation number 4, to help us out. So let's start with our first case. Case number 1. X naught is equal to y naught, which is equal to 0. So plugging this information into that last equation, equation number 4, 0 to the 4th plus 0 to the 4th plus z to the 4th minus 1 is equal to 0. Z is equal to plus and minus 1. So I have 0, 0, 1, and I have 0, 0, negative 1. Case number 2. It's going to be similar to the one I just did in terms of letting the other variables equal 0 and then one that is not. So case number 2 is when x naught is equal to z naught, which is equal to 0. That will give me y is equal to plus and minus 1. So I have 0, 1, 0, and I have 0, negative 1, and 0. Case number 3. Case number 3. This is when z naught is equal to y naught, which is equal to 0, which tells me that x naught, and this is x naught, and this is z naught, is going to be equal to plus and minus 1, and so I have 1, 0, 0. I have negative 1, 0, 0. Cool. Now, up until now, I haven't had to find lambda. It wasn't part of any of the cases. It was not part of the choices that I was choosing. Now I'm going to choose case number 4, in which x naught is equal to 0, and then y naught is equal to z naught, which is equal to, and plus or minus 1 over 2 lambda, the square root. It doesn't matter which I choose plus or minus, and the reason is because I'm going to raise it to the 4th power. Because I'm going to raise it to the 4th power, the square root, the negative, so I have 1 over the negative square root of 2 lambda. When I take it to the 4th power, will give me the same value as if I have 1 over the positive square root of 2 lambda. So for sake of argument, I'm just going to call that 1 over 2 lambda. And once again, I'm going to be putting this into my 4th equation. So I have 0 raised to the 4th power plus 1 over 2 lambda, the square root raised to the 4th power, plus 1 over the square root of 2 lambda raised to the 4th power is equal to 1. On the left-hand side, I'm going to get 2 over 4 lambda squared is equal to 1, which tells me I have 1 over 2 lambda squared is equal to 1. That tells me that lambda is equal to plus and minus the square root of 1 over 2. Now, when I put this back in to this part of the equation, I clearly cannot take the negative. So, because I'd be taking the square root of a negative number, so I can only take the positive. So then y naught is equal to z naught, which is equal to 1 over the square root of 2 times the square root of 1/2. Now, let's talk a little bit about the algebra. Nice little refresher here. This is 1 over, I'm going to write this large, so it's going to be 2, and then I'm going to rationalize the denominator, so it's going to be the square root of 2 over 2. And then what ends up happening is that I have 1 over the square root of 2, which if I write this as 1 over 2 raised to the 1/2, this gives me 1 over 2 raised to the 1/4. And so in other words, this is equal to 1 over the 4th root of 2. Okay? So I just want to take a moment to do the algebra. I know you're like, I know, I remember, but I just want to give it to you anyways. And so what I have now is 0, 1 over the 4th root of the square root of 2. And I also have 1 over the 4th root of the square root of 2. Similarly, for case 5, so case 5, I'm going to let that one, I let x equal 0. I'm going to let y equal 0, and then I have the x naught is equal to the z naught, which is equal to 1 over the square root of 2 lambda. Again, it doesn't matter if it's plus or minus. And so I will end up with the same kind of thing where I've got 1 over the 4th root of the square root of the 4th root of 2, 0, and 1 over the 4th root of the square root of 2. Case number 6, this is where I'm going to have z naught is equal to 0, and y naught is equal to x naught, which is equal to 1 over the square root of 2 lambda, which gives me this ordered triplet, which is 1 over the 4th root of 2, and then 1 over the 4th root of 2, and then, of course, 0. Now, we are not done exhausting the cases. The last case is case number 7, in which everything is the same. So in case number 7, x naught, which is equal to y naught, which is equal to z naught, which is equal to 1 over the square root of 2 lambda. Putting this into the fourth equation, we're going to have 1 over 2 lambda, the square root raised to the 4th power, plus 1 over the square root of 2 lambda raised to the 4th power, plus 1 over the square root of 2 lambda raised to the 4th power, which is equal to 1. When I get done with this, I'm going to get lambda is equal to the square root of 3 over 2, which tells me when I get done with the algebra, x naught, which is equal to y naught, which is equal to z naught. Well, actually, it's not true because I can take combinations of it. So x naught is equal to plus and minus 1 over the 4th root of 3. Y naught is equal to plus and minus 1 over the 4th root of 3, and z naught is equal to plus and minus 1 over the 4th root of 3. So this ordered triplet is a multitude, right? Now what I want to do is I want to find where my minimum and my maximum happens. So I go back to my original function, which is this lovely function right here. And I'm trying to figure out which one is going to produce the minimum and the maximum. Now, I have all of these choices, and I know that the minimum would happen when this thing is equal to 1, because that is the choices of when I have 0, 0, negative 1, or I have 0, 1, 0. I know that these are going to produce the smallest because when I put one of these other choices, and one of my other choices is where I have the 1 over the 4th root of 2 and the 1 over the 4th root of 2 and 0. When I put it in here, I'm going to get 0. And then I'm going to have plus, and I know that when I square the 4th root, it'll be the square root, and I have 1 over the square root of 2, plus another 1 over the square root of 2. That's larger than 1. So I know that my minimum is going to happen, so that my minimum is going to be happening when I've got one of those cases, case 1, 2, or 3. So when I have a 0, 0, positive and negative 1, or 0, positive, negative 1, 0, or positive, negative 1, 0, 0. The minimum is going to happen, and what the minimum is going to be x, y, and z. Minimum, it will be 1. Now, the place in which I'm going to have the largest, my maximum, is when I'm going to be having the cube root. So that was my very last one over here, which was 1 over the 4th root of 3. That's going to be my maximum. And so I have f of x, y, and z. This is going to be happening when I have 1 over the 4th root of 3, the quantity squared, plus 1 over the 4th root of the 4th root of 3, the quantity squared, plus 1 over the 4th root of 3, the quantity squared. And what my final answer is going to be is the square root of 3. So I found my minimum and I have found my maximum. This was a long problem because I had a lot of choices. There's a lot of choices going on here. Now, let's take a look at this one. This is an example in which I have 2 constraints and I have 1 function. But the good thing is that it isn't going to be as bad as my previous example where I had a lot of choices to have to blow through. So the first thing I'm going to do is find my gradient of f. So this is x, y, and z. So I'm going to do my first derivative with respect to x, which is just going to be y. My derivative with respect to y is going to be z plus x. And then my derivative with respect to just z is going to be y. Now I'm going to do my gradient of g. I'm going to call this g. G of x, y, and z is going to be equal to x, y minus 1. So my gradient of g is going to be equal to my derivative of, with respect to x is y, with respect to y is x, and then 0. To my last one, the gradient of h, which is, I'm going to rewrite this as h and I wrote g, h of x, y, and z as y squared plus z squared minus 1. I have no x, so that's going to go to 0. And then it's going to be 2y and then 2z. Now remember, I have the gradient of f is going to be lambda sub 1, the gradient of g, plus lambda sub 2, the gradient of h. So I'm going to have y naught is equal to lambda sub 1, y naught plus lambda sub 2 multiplied by 0. So here's my first equation. Normally I like to set out all my equations to begin with. So here's my first one. I'm going to label this as number 1. Number 2 is going to be my x naught plus z naught is equal to, so z naught plus x naught is going to be equal to lambda sub 1 y naught, or excuse me, this is the second term. So this is going to be x naught, and then plus lambda sub 2 multiplied by the 2y naught. My third equation is going to be y naught is equal to lambda sub 1 times 0, that's nice, plus lambda sub 2, and then I have 2z naught. My fourth equation is setting my g function equal to 0. And so I have my g function, which is x naught, y naught minus 1 is equal to 0. My fifth equation is going to be setting my h function equal to 0. And so I have y naught plus z naught, and that should be y naught squared plus z naught squared is equal to 1. Okay, so my unknowns, I have x, y, and z naught, so that's 3 unknowns there. Lambda 1 and lambda 2, that makes 5 unknowns. I have 5 equations and 5 unknowns. And I'm going to let you all solve these, and I'm just going to go right to the answer so I can tell you all the possibles that we have. Now, from this equation, we're going to get lambda sub 1 is equal to 1. So we've already eliminated one of the possible unknowns. We now have that. Doing some more manipulations, we're going to get lambda sub 2 could equal plus and minus 1. We also get that y naught is going to be equal to z naught plus or minus. So this is the choices that we're getting. And we get z naught to equal plus and minus 1 over the square root of 2. And so let's start with the iteration. So if z naught is equal to 1 over the square root of 2, then y naught is going to be plus and minus 1 over the square root of 2. And that x naught could equal plus and minus the square root of 2. So I could have square root of 2, 1 over the square root of 2, 1 over the square root of 2 as a possible choice. I could have square root of 2 minus 1 over the square root of 2, and 1 over the square root of 2 is a possible choice. And I could then have the negatives. Negative square root of 2, 1 over the square root of 2, 1 over the square root of 2. And then I have the negative square root of 2, negative 1 over the square root of 2, and 1 over the square root of 2. So those are my ordered triplets for just z naught equaling 0. Similarly, if I let z naught equal 1 over the negative square root of 2, then my y naught could equal plus and minus 1 over the square root of 2, and my x naught could equal plus and minus the square root of 2. All right, so I would have to choose all of these. I have bunches of these to test. And I would test these by my usual way of testing for maxima and minima. A lot of work. What I have when I get done, though, is my maximum is going to happen. My max will happen at f of square root of 2, positive square root of 2, 1 over the square root of 2, and 1 over the square root of 2, which gives me a maximum of 3 over 2. The minimum value happens when I have the negatives of each one of these, which gives me a minimum value of 1/2. So here's my maximum value, and here is my minimum value. Let's take a look at this next one. You're probably wondering, wow, she gave us a lot of space. Well, it's because there's a lot going on with these. Math-wise, not hard, easy to get caught in the weeds. So organize your possible ways of finding the solutions in a way that is easy for you to follow, which means it'll probably make it easy for me to follow. Now, once I got down to here, I threw all of this stuff into a matrix because I like matrices and I'm pretty fast on my calculator, and so I put it into a matrix that gives me all of this stuff. So you can do back substitution, you can do matrices, you're going to do whatever is most convenient and easy for you to be able to solve. Let's take a look at this example. It's slightly different, where I'm asked to maximize when I have x is equal, or I've got these another two constraints, and I'm asked to, minimize. So they're telling me out of the gate, I want to minimize this. So starting out with the fact that I need my gradients, I'm going to start with the gradient of f. I'm going to call this g of x, y, and z. And I'm going to call this h of x, y, and z. So my gradient of f is going to be equal to 2x, 2y, 2z. My gradient of g is going to be equal to 1, 1, 1. Ooh, we like it when that happens. And then my gradient of h is going to be equal to 1, 2, and 3. Oh, that's even better. That's nice. That's really nice. So, starting with my first equation, we have 2x naught is equal to lambda sub 1 times 1. plus lambda sub 2 times 1. My second equation is 2y naught is equal to lambda sub 1 times 1 plus lambda sub 2 times 2. My third equation is 2z naught is equal to lambda sub 1 times 1 plus lambda sub 2 times 3. My other equations are, let me see, x naught plus y naught plus z naught is equal to 9. So that is my fourth equation. My fifth equation is x naught plus 2y naught plus 3z naught is equal to 20. And solving in my usual shenanigans, I'm going to end up with x naught equaling 2, y naught equaling 3, and z naught equaling 4. And so my f of 2, 3, and 4, putting that back into the original equation, produces 29, and that is my minimization. Let's take a look at an application problem, and you'll notice on the notes I gave you plenty of space to do your work so you can get the same answers that I got. I'm not going to bore you with going through finding the answers by using various methods to solve, whether it's back substitution, elimination, or matrices. We want to find the minimum and maximum distances between this ellipse and the origin. Now, what we know is that this ellipse is a rotated axis ellipse because we have this xy term. So our distance is d squared is equal to x squared plus y squared. That's the thing we want to maximize. That is our function. Now, I could take the square root of both sides, but that means it's going to be a little bit more interesting when I do the partial derivatives. And what I'm going to just do at the end is I'm just going to find my distance, and then I'm just going to take the square root of that answer. So I'm going to write f of xy as x squared plus y squared. And that is the function that I want to minimize or maximize. The thing that is going to constrain me is this. So that actually is my g of x, y. So g of x, y is going to be this equation, which is x squared plus xy plus 2y squared minus 1. Then I'm going to do my usual partial derivatives. So the partial derivative of f is going to be equal to 2x plus, and then 2y. I don't know why I want to do plus, it's just 2y. And of course I should have that. My gradient for g of xy is equal to, let me see, I'm going to have 2x plus y, and then I'm going to have y plus 4y. And I'm going to set them equal like I normally do with my lambdas. So I have 2x naught is equal to lambda. And I only need one lambda here. 2x naught plus y naught. And then I'm going to have 2y naught is equal to lambda y naught plus 4y naught. So equation 1, equation 2. My third equation is the fact I'm going to have x naught plus x naught y naught plus 2y naught minus 1 is equal to 0. So there's my third equation. My three unknowns are x naught, y naught, and lambda. And so I'm going to go through my usual solving, whether it is by doing substitution or elimination. It's totally up to you how you want to do it. And I ended up getting x naught squared is equal to, I have 3 plus and minus 2 root 2 all over 4 plus and minus root 2. So a whole bunch of choices. And of course, any of these that produce a negative number, you would go ahead and toss. So then I got y naught squared to be equal to, I ended up with -1 plus the square root of 2 squared multiplied by my x naught squared. And I actually have plus and minus, so I have plus and minus on that too. So I have a bunch of choices. So my distance max, when I get totally done, ends up becoming the square root of 12 plus 4 root 2 over 14. And my distance min, when I get totally done, is going to be the square root of 12 minus 4 root 2 all over 14. And so those are my two answers. A lot of work. 3 equations, 3 unknowns, some really kind of unpleasant answers, but not bad, not fun, but not bad. Okay, again, a lot of space for your work. Let's take a look at this example. We have a large container in the shape of a rectangular solid must have a volume of 480 meters cubed. The bottom of the container costs $5 per meter squared to construct, whereas the top and the sides cost $3 per meter squared. Use the Lagrange multipliers to find the dimensions of the container. So the first thing that we have is x, y, and z, assuming that we have 3 different variables for x, y, and z. This needs to equal 480. And that's our constraint function. This is our g of x, y, and z, because we know that this thing has to be no larger than 480. And in fact, it has to have a volume of 480. Now, we have to figure out the cost to construct it, and that's our function. That's the function we're going to minimize or maximize. So the function that we need to minimize or maximize has to do with the cost of constructing the box. So we have this box. I always like to draw pictures. The bottom of the container cost $5 a meter squared. So if this is x and this is y, then it's going to cost x times y, which is the area of the base, times 5. That's going to be the cost of the base. Then I'm going to have my my sides. And if we call this thing z, then I'm going to have one side that's going to be plus. I'm going to have 2 sides that are going to be x and y, y and z. So 2 sides are going to be y and z. And then its sides are going to be $3 to construct. And then I'm going to have and then times 2. Because I have 2 of those sides. And then I'm going to have 2 of the sides that are x and z, and it's going to cost $3 to construct. Now, I also have the top, right? And so constructing the top is going to be xy, so plus xy, but it's going to have a cost of 2. So my function, x, y, and z, is the thing in which I'm trying to minimize the cost. It's going to be equal to this 5xy and this 2xy, so that gives me a total of 7xy, and then plus 6yz and plus 6xz. So these are the constraints that I want to minimize. And this actually, let me go back, this should be not 2, it's 3 here, which means this is 8. So this is 3, and this would be 8. So I want to maximize or minimize these. So again, I'm going to go ahead and do my gradient. So my gradient of f is going to give me, in terms of x, I'm going to have 8y plus 6z. And then in terms of y, I'm going to have 8x plus 6z, and then my z is going to give me 6y plus 6x. My gradient, so my delta g is going to be yz, xz, xy. All right, so start with my equation. Equation number 1, 8, it's a terrible 8, 8y naught plus 6z naught has to equal y naught z naught. My second one is my 8x naught plus 6z naught has to equal x naught z naught. My third one is 6y naught plus 6z naught, don't forget your lambdas, has to equal x naught y naught lambda. And then my last equation, my fourth equation, is x naught y naught z naught has to equal 480. 4 equations, 4 unknowns. You're going to solve however you like to solve. And we're going to end up with the answer of x is going to be equal to y, which is going to be equal to the cube root of 360. And z is going to be equal to 4, the cube root of 360 divided by 3. And that is the dimensions that you're going to need to minimize the cost of this container. I think that's it. I think that's my last one. Yeah, that is my last one right there. Again, the hardest thing about this, I think, is going to be keeping track of your equations and solving them. So this will be a nice refresher on solving equations, whether it's elimination, substitution, or if you can, in matrices. And that's it for this section.